Welcome to lecture 4 of the course Operating System. With this lecture, we begin our second module, Process Management, and this is the first lecture in this module. In this lecture, we'll be introducing the concept of process. We'll see how to work with process and what constitutes it. So let's begin this lecture by first defining a process. So what is a process? It's an abstraction of a running program provided by an operating system. That is, whenever a program starts executing, we call it a process or a program in execution. Now, why does the operating system create this difference between a program and a process? Well, to understand that, we should know how does a program execute. Okay, so let's say this is a program. What is it? A set of instructions, or you may say, so this is a program, and what constitutes a program? Some code or instructions and some data. Okay. Now this set of instructions or the code and the data that I have written here may be written in a language of the machine on which we would like this code to be executed. We call that as machine level instructions, or it may be written in some language that is suitable to me. For example, I have written this code using a language called C. So that is called a high level language. But if you write a program in a high level language, you ultimately have to translate that into the language of the machine. And to do that, we take help of a software called compiler. So a compiler translates this high level program into the machine level code. Okay, so a compiler, it converts a high level code into machine level code. So let us say we are using a Linux based system. So at the Linux shell, we type in a command called GCC and we provide to GCC this code which is written in a high level language, and we ask it to compile. So if you don't have any error and if the compilation is successful, what you get is the machine code of this program in high level language. Let us say the machine code is a program called a.out. So this code that we obtain is called the executor. So we will assume that our program has been obtained in the form of machine level instructions. That is, we have this executable. And where do we have this executable? We have it in some secondary storage device. So our executable, which is the code and data, is present in some storage device. So here we have this code and data, and this is my a.out code. Okay. So now we would like this a.out to be executed. Who executes that? It's the CPU which will be executed. And how will you execute this? Okay. So if at that same Linux prompt you type in a command called /a.out, you are actually instructing the CPU to execute this code and data. But what happens before this execution? The CPU, as you know, would only execute instructions which are available in the physical memory. That is, in this RAM. So this is the physical memory. If you have to execute this code, we would have to bring this code and data and place it in this memory. So now this is my a.out, and this is the code and the data that we have loaded. Okay, so we load this executable into the physical memory, and then by this command we instruct the CPU to execute this code and data. So the CPU knows the range of addresses within which this code and data sits. It fetches each one of them and it executes. So the CPU fetches, executes, then fetches the next, then executes, and in this way it executes all the instructions present within this range of memory locations. So this is how a program executes. Right? Now let's try to go a bit deeper and see what happens when this program starts execution. So let us assume that this code and data, that is our a.out program, is here. Let me write it as a.out, my code and data. Okay, so this has been loaded. Now, when we want the CPU to execute this, is during execution, now it's not only that these instructions which form the part of this code and data, they get executed. During their execution, we have certain instructions which allow or which ask for allocation of some space. Say for example, this particular instruction or maybe this instruction. Okay, so these instructions ask you to allocate some space where the CPU would be storing some data. This particular line refers to allocation of a space to store something called an array by the name buff, which means that there must be some space which must be allocated so that you can hold this array. Okay. Then this line, this is one again way by which this particular process or this particular program, it asks to allocate some space which it will be utilizing during runtime. Maybe it will be holding some data there. Okay, so there must be some space which must be allocated, which will be used during runtime. Okay, so this space will be used for runtime allocation. So you see, it's not only the space that is occupied by code and data, but during the execution of instructions, there may be requirement of space, whether to store some data before instruction, before compiling, before execution, or during execution. So there is a need for this space. Right? In addition to that, there may be such kind of executions which involve a function call, right? So if it is something of this type, then the execution of this current program stops and you jump to some other program. And if that happens, then you must save the current state of the program. That is, if you jump from main to F1, you must save the state of F1 before you jump to save of state of main before you jump to F1. And you must also save the return address after you come back from F1 to main. So all this also requires some space where you will be storing all these contents. And we know that the way to do it is a space called stack. So that means, apart from the code and data that resides in the memory, a program execution requires some additional space. And this is where the OS comes in the picture. So before the program executes, what the operating system does is, it allocates some space to that particular program. Okay? And this space that it allocates is used for different purposes. Either it is used to maintain the stack, or it is used for dynamic data allocation, or it is maintained to store some variables. So this amount of space that the OS allocates to this process, okay, that gets added to the existing code and data. So what the OS does is, the OS, it allocates the memory to the process prior to execution. That's what it does. Okay? And once this particular space has been allocated, it makes this space available to the process, and now this entire space along with the code and data that becomes part of the process. And once this entire memory space becomes part of the process, now this range of address that you have is called its address space, right? Or maybe we can, for the time being, let's forget about it. We will call it the memory image. Okay? Memory image of what? Memory image of the process. So if the process is a dot out, this a dot out process now has this memory image, which contains the code and data and some memory space that the OS has allocated to that particular process in order to store different things, either the stack contents or the dynamic data or the variables, all this, right? Now, interestingly, apart from all this space that is used up by the process, you find there can be instructions such as this, and this is a system call, and we already have studied that these kind of instructions cannot be executed by the process. It can only be executed by the kernel. That means that there must be some space which the kernel will also be utilizing in order to execute the instructions for the process. Okay, so that means there must be some space allocated to this process which will be utilized by the kernel. So let's say this is for the kernel space. Now, the entire range of address thus allocated to the process by the OS, this entire thing, which holds this memory image, is called its address space. So this is called the address space. Right? So the entire range of locations, or this entire memory space that is allocated to a process by the OS, is called its address space. And this is the range of locations within which the process will be updated. All the contents of the process will be updated during the execution. So that is how the OS will be keeping track of what is going on in the process. Some part of this address space will be used for execution of the user code or the data that is updated during the user code execution, and some part of that will be used for maintaining data which is executed by the kernel, such as these. But in total, the entire thing is what you call the address space. Right? So this is what happens during a program execution, and that is the reason why we need to treat the running instance of this program separately, because when the program runs, it's not only the code and data, but there are a lot of other things that add up to this code and data, and they have to be maintained. So when the program starts executing, it actually affects the machine states, and these states that this particular program during execution affects is held in some additional space along with this code and data, and together that's what makes up a process, or the memory image of a process. That is the reason why OS treats the program and the process differently. Okay, so now that we have seen how a process gets loaded onto the memory and how OS allocates space to the process, let's go in a bit details to see what constitutes a process. Okay, we already have seen that, so let's look at it again. So when a process is loaded onto the memory and the process before its execution, OS does a couple of jobs. And what it does is it allocates some space to that particular process, and that space that it allocates becomes part of the process. What is the space that it allocates? So the code and data, so this portion is already there in the memory when this is loaded. Okay, so this is, now apart from that, we saw that there are situations where you need some function calls may happen. Say for example in this, so the parameters have to be passed, the return addresses have to be saved. So what the OS does is it makes use of the stack area of the program and allocates that to the process, and we know that what this stack is used for. Even after the stack is being allocated it fills up the stack by the parameters of the main function. So it fills them up so that it can be utilized during the execution. Then there can be situations. So say this is where the stack is utilized for. Now this portion is utilized. This is something where you have the allocation of space at one time, and we have in C this is done by using these kind of instructions. So the OS makes use of the heap to allocate that space, and that space is now currently allocated to the process. So okay, in addition to that, there are situations, there are instructions which the process is not allowed to execute. They have to be executed by the kernel, and kernel during execution of these kind of instructions may require to require to jump from one function to the other, so it may also require some stack. So that is why some portion of the kernel stack is allocated to that process, and there is some portion where we keep track of what is going on in the registers during the computation or during the execution of the process. So as a result, the register values also have to be saved. Some important registers such as the program counter, the stack pointer, and some other registers in the CPU, their contents of that must also be saved. But then again, saving of this is also a privilege which is only done by kernel. So you see that some portion of these kind of instructions. Sorry, so this is part of the kernel space. So some portion of that is executed by the kernel. So this is the total amount of space that is allocated to a process. Okay, and we already have seen that this entire thing is what we call the address space. Okay, and this is known as the memory image of the process. Okay, so what if the once this the OS has created the address space of that, and now it has built the platform to execute or to start execution of this process. And how does the process execution start? Well, the first address of this address space is loaded onto the program counter of the CPU, and the CPU then starts executing each one of these instructions one by one. Once we know how a process starts execution and how the OS helps the process in execution by allocating some space, now let's see what happens during execution. So we are going to talk about the process states, that is the life cycle of a process, and how a process goes through one state to the other during its execution. So when a process begins, that is, you just started executing the process, we say that the process is in the new state. Okay, so that is, a process is created. So it is just being created. We say that it is in the new process. Okay, now once the process has been created, we saw that the next step is it has to be loaded onto the physical memory. Okay, so the newly created process now is loaded onto the physical memory, and the OS has allocated the space, that is the address space of the process is now ready, and it has initialized whatever it needs to do in that particular address space, such as some values in the stack, etc. And the process is about to run. So we say that the process is ready to be executed. Okay. Now, once the process becomes ready to be executed, and you instruct the CPU by the first address of that process, and the CPU starts executing that. So when the CPU starts executing the process, we call that the process is in the run state. That is, when the process starts execution. So then the CPU reads every instruction starting from the first location. It executes, moves on to the next one, and in this way, when it reaches the last instruction that it has to execute, it executes that, and then we say that the process has terminated. That is, it has finished its execution. So that is the life cycle of a process. A process gets created, it gets all the space and all the the OS allocates all the space necessary for that particular process to run. The process is ready to be executed. It starts execution, and when the CPU completes the execution of all instructions, it terminates. Okay. But there is something that happens in between. What is that? Now there are instructions during the execution of the process. There are instructions which the process is not supposed to execute. We know what these instructions are. These are called system calls. What are they? There are some special instructions, such as the hardware access instructions, and the process wants to execute them. But since it is not privileged to do, the kernel executes them on the behalf. Now when the kernel executes them, obviously the process does not run on the CPU. So in that case, the process is set to go into a wait state. So it's set to go into a wait state. When that particular process has made an IO request, let's say. So that same kind of an open system call. Remember in this code that we had in this a.out code, okay, we had this open system call. So this is nothing but a request to the kernel to execute that on behalf. So during this time, the process has to stop. It has to go into and wait until this IO request is over. So when the IO request is over, then it is again put back into the ready state. So this is how you see that a process moves from one state to the other during its entire life cycle. Now interestingly, during an execution of a particular process, there can be other processes which would also like to run. And if you go back to the first lecture, we said that in case of a multi-programming environment where let's say two processes, they are currently in the physical memory, and if say a process called P1 which was initially running suddenly goes into a wait state, it has just made a IO request, okay, it has made an IO request, here it has made an IO request. Now in order to prevent the CPU from remaining idle, it was suggested that if there is one more process which would you like to run, you may allow the other process to start its execution. So that means there must, instead of wasting the CPU cycles during the time when the P1 was in the waiting state, you may allow other processes to run. Now how do you know? And this can be not one but many processes. So now if there is a lot of processes which are ready to be run, how do you decide who will run? So what you do is you maintain some kind of a data structure. We usually call it the queue, and we hold all the processes which would like to be run. And obviously the one which is at the head of the queue will be the one that will be given a chance to get executed during the time when P1 is not running. How to decide who will come at the head of the queue, etc. will take up in the lecture related to process scheduling. So presently, let's try to understand, or let's summarize that a process when it starts executing moves from one state to the other, and in between when it requests for an IO, it may go into a wait state, and when the IO request is over, it is again put back to the ready state. So these are the different states of a process. Now we'll talk about an interesting concept called virtual memory, and we'll see how the address space of a process, how it gets mapped to the physical memory. Where does it locate, how the OS keeps track of that, and what is the view as seen by the programmer or the CPU. Okay? So we know that whenever a process gets created, the OS allocates certain space to that particular process, and that's what we call the address space, and this is the content of the address space of the process. We call that as a memory image. it contains the code and data. Some space it keeps for handling the stack related data, some it keeps for dynamic allocated data. It keeps track of what is the state of that particular process in the OS, and then finally we discuss about it allows the kernel to execute some code, so kernel may require some stack. So as a result, it keeps some space for the kernel. So this is what makes up the address space. Now this address space that the OS allocates is called a virtual address space. Why do we call the name virtual? Because it's not the actual address which where the process sits in the physical memory. It's the view which is seen by the programmer or the CPU. Now you may wonder, why do we have to have this two views? Okay, so here the memory image that you see in the physical memory, okay, this is say the memory image of the process, say a process. This is the actual physical location of the process, the physical location of the address of the memory image. This is the physical address, and this is the virtual address. So the question is, why do you need to have two addresses? We'll come to that in just a minute. So for the time being, let's assume that the OS allocates this range of address. And what is the maximum range that can be allocated? That depends on the machine. Which machine? The computer, obviously. So say a machine with 32-bit registers, okay, will allow 2 to the power 32 addresses, will allow 2 to the power 32 virtual addresses. What do I mean by that? So you remember there are certain, what does a CPU contain? It contains some registers. Okay, so registers are storage locations. Out of that, some registers are meant to generate address. One of them is the program counter that generates the address for a particular memory location. And say if a program counter is of size 32-bit, okay, so the number of addresses, number of address patterns that can be generated, or number of binary patterns that can be generated by this program counter will be 2 to the power 32. And each pattern corresponds to a particular address location. So at max, you can have 2 to the power addresses that can be generated. And 2 to the power address means about 4 GB. So you can have a maximum of 4 GB space that you can allocate for a particular process. Okay. But this address that I am talking about is a virtual address. So let's say our machine is a 32-bit machine, so our process can at max have a space of 4 GB allocated to that. Now, interestingly, every process that you create can have a 4 GB size. So let's say this is process number 1. Similarly, I can also have another process. So this is process P2, which also has the same. So this is say process P1, the virtual address space of process P1. This is the virtual address space of process P2. This will also have its own code, data, then we'll have the stack, the heap, okay, another kernel stack, the state. So this will also have its memory image. And this can also have a 4 GB. Now you see, the interesting thing that happens by using these virtual address spaces, there is no restriction in the amount of addresses that you can generate or allocate to a particular process. If you have allocated a process of 4 GB, it doesn't mean that you cannot allocate a 4 GB to another process. You can allocate a process P2 with the same location or with the same range, okay, as many processes as possible. So processes can be of any size, obviously restricted by the size of the machine. So there can any process can have you can allocate a space of 4 GB to it. Okay. But what is the basic utility of using this virtual addressing? What do we get out of that? Let's see it. Now we said that the virtual address is the view that the CPU or the programmer has about a particular process, right? But remember that this memory image that you create of the process actually has to reside in this physical memory, okay? And there lies the problem. So what is the problem that we have? The problem is that think about a situation where you would like both processes to be there in the physical memory, and let's say both of them are of size 4 GB, right? But you do not have sufficient amount of memory to hold both processes. What is it? Let's say you have your physical memory which only has 2 GB space. Okay? So how will you hold both the processes? That's a major problem. So what we will do is, at this, we know that the processes, they are initially in the hard disk, right? So suppose if this is of 4 GB size, what we will do is we will split this up into 4 parts, each of 1 GB. Similarly, this will also be of 4 GB size. Let's say this is P1, and this is P1, and this is P2. So we'll also split this up into 4 parts, and each is of 1 GB. And because this allows only 2 GB space, okay, we will allow the first block of P1 to be loaded here. Okay, this is 1 GB, and this will be P1. And the next 1 GB space will be occupied by the first block of P2. So in this way, we are allowing both the processes to be present in the memory, while we don't have any problem of space. But does it work? Yes, it works, because when the CPU would be executing this process P1, it will not be executing the entire 4 GB. What it will do is, it will execute that in blocks. It will execute the first part, then the next part, because you don't execute the program at once, isn't it? You execute some part of that, then the next part, then the next part. So obviously when the first 1 GB is done, this 1 GB will come back here, and the next 1 GB will be replaced here. Similarly for P2. Okay. Now, or it may so happen that the first 1 GB of space of P2 is over, then you bring the next 1 GB, and this 1 GB will be replaced by the next 1 GB of P1. This can also happen. But if this swapping in and swapping out of these blocks of processes go on in the physical memory, it becomes very difficult for the CPU to keep track of that. Right? And when you write your program, as a programmer, when you want to write your program, in that case, if you are working with some particular address, okay, you get confused where to and which particular address should I choose, because you see the P1 initially, the first block was sitting here, the next block is sitting here, maybe then P2 comes here, the third block again comes here, so it will be all jumbled up, right? So the process, because it's not one single block of a process that is sitting in the memory, they're coming in blocks, and these blocks may switch their positions, which means that if you look at the physical memory that you are looking at, the processes that are sitting in this particular memory at any point of time, they may be sitting in a distributed way. That is, let's say this is P1, some part of P1 is here, some part of P1 is here, some part of P1 is here. Whereas the P2 may be some part of P2 is here, some part of P2 is here. So you see, it's a complete distributed way of storing the processes in the physical memory. So this is the physical memory. Okay. So it's okay, it's very advantageous, because it will allow you to have multi-programming. Many processes can be sitting at the same time. You don't worry about whether your process is not fitting into the physical memory because you are bringing them in blocks. But the problem that happens is, since you are bringing them in blocks and the blocks are sitting anywhere in this entire memory, it's kind of a distributed storage. But the CPU, if it has to access a particular process, say P1, it has to know each of the blocks, their actual locations. And that is the problem. Because it has to keep track of the exact location of P1. And writing this kind of program, where there's a chance that the blocks can shift their position, is very difficult. So in order to avoid that, why can't I have a view of the process which does not have this kind of distributed storage? That means it feels that this entire, the range that has been allocated to a process is continuous. And that is exactly what this virtual address space is. So it's nothing but a contiguous address range allocated to the process. Okay, and this is the way that is seen by the CPU. So what the CPU does is, whenever the CPU puts a request for some instruction by providing an address, because it does not have a view of this physical memory, what it sees about process P1 is this range of address. So it does not have to bother about the actual location of that particular process in the physical memory. It feels that the entire memory, 4 GB memory, is available and that has been occupied. It doesn't know that the physical memory is actually 2 GB size. The entire seems that as if entire 4 GB size memory is completely occupied by process P1 and the entire process is available to me. So whatever address it sends for a certain instruction, okay, so this address that it generates is actually a virtual address. Okay, so the CPU is actually looking for an instruction, thinking that the address that I am looking for or I have generated, the entire data is available to me. It doesn't have to know the actual address. Now it's the responsibility of the operating system, okay, to interpret this address and find out that the address that this particular CPU is looking for corresponds to which physical address. So it may be somewhere here that this instruction resides in the physical memory. So the logical address or the virtual address that has been put by the CPU, the OS translates that into the physical address of the instruction. It fetches that instruction and provides it to the CPU. So this is how the OS plays a role in translating the virtual address to a physical address. Okay, so let us quickly summarize. So the memory image that is created of a particular process has two views. One is the actual location of the memory image which sits in the physical memory, but that memory image is not contiguous. It can sit anywhere in the memory and it can be split up into blocks, and these blocks can be distributed all through the physical memory. So as you can see in this diagram. But the problem of accessing such kind of distributed blocks is that the CPU has to know the exact location of that particular block, and that is why it becomes very difficult. So in order to avoid that complexity to the CPU, what the OS does is it creates a contiguous view of that same process, and this is the view which the CPU sees. So the entire memory address that is seen by the CPU about the process is a virtual address. It's one single memory, all contiguous locations, and the range of addresses that the particular address map can be allocated, it depends on the machine. Okay, so once this allocation has been done, the CPU, when it generates an address, generates the address keeping in mind or keeping in view the virtual address map. So obviously the address that is generated is a virtual address, but the virtual address is interpreted by the operating system, and the operating system in turn understands what that corresponding address means in the physical memory. It goes to the physical memory, accesses that instruction from there, and provides it to the CPU. So this is how the virtual memory helps. But now let's go a bit deeper and try to find out how the OS performs this translation. So that is important. Okay. There are many methods by which this translation can be done. We will be talking about one of them, and the concept that we are going to talk about is called paging. We will take up this in more details in the memory management module, but in order to discuss some concepts which are going to come next, I'll quickly discuss this paging concept so that you get an idea of how virtual addressing and physical address they are related. Okay. So we found that a process is allocated address range, and this address range that we allocate to a process, the OS that allocates this to a process, is called its virtual map. Right? So it's the virtual address. And the OS, it maps this to its actual location in the physical memory. Okay, and how does this take place? Let's talk about that. Now what we do is, the virtual address of a process that we have, we split this up into equi-sized blocks. We split the entire virtual address range of this process into equi-sized blocks, and these blocks are called pages. They are called pages. Now, how many pages, that depends on the programmer, or how many pages you would want. It varies from OS to OS, where you decide that what should be the size of this page, etc. So for the time being, let's try to understand that. Okay, the entire address range will be divided into equal-sized blocks, and these blocks will be called pages, and every page will have an index associated to that, and we call that as the page number. Okay. On the other side, the physical memory, we can also assume that has also been split up into block of addresses, and this block of addresses here will be called frames. So similarly, frames will also have their index associated. This is frame number 0, frame number 1, 2, 3, 4, 5, 6, 7, something of this sort. And we put a constraint that you have a page size equal to a frame size. That means every page can exactly fit into one frame. Okay, so this is the constraint we put. Now, what the OS does when a particular address or virtual address is put by the CPU. So the CPU has, let's say, requested for a particular address. Now, when it puts a particular address, that may belong to, an address means a certain location that will fall in any one of those locations in the virtual address, and that particular location may belong to any page. So let's say the address that this particular CPU has put falls in this block of addresses. That means it falls in page number 1. Okay, and this page number 1 maybe resides here. So this is where, let's say, your page, that particular page number 1, that resides here. So what you need to keep, you just need to keep an index related to where this page number 1 resides in the physical memory. It resides in frame number 3. Okay. And this indexing is what is maintained in a table. So this is a table, and what this table contains is some entries. How many entries? Entries corresponding to the number of pages. So you have the index of this table, which corresponds to the page numbers. So page number 1 corresponds to this entry in this table. And what do you have in this is the frame number, which is frame number 3. Okay, so that means any address which falls in page number 1, if you look up in this table, you know where that page sits in this particular physical memory. That's it. So that is how you maintain. Okay, there is something more in this table. We will talk about that when we come to the memory management unit. So for the time being, we just try to understand that what OS does is, OS looks up this particular virtual address and it looks up in this table to find out, oh, this corresponding address means frame number 3. And it goes to frame number 3 and brings the address from here. Okay. So this table that the OS looks up is called the page table. And this is how the OS manages to have a translation of a virtual address to a physical address. So the frame number that comes out is the physical address. The details of this translation, I'll talk about that again when I come to the memory management unit. So it was to keep a continuation, we just discussed about that. So this is how an OS maintains a relation between the virtual address and the physical address. Okay. Now, and one more advantage that we have by using this physical address is, you see, when we discussed about the virtual address, if you remember, we said that the memory image of this particular of every process, some part of that falls in the user space and some part it falls in the kernel space. Okay. What do you mean by this kernel space? The kernel space, when I say kernel space, I mean that this range of addresses in the virtual address per process, they are actually mapped to, in the physical address, in the physical memory, to the portion of the kernel in the physical memory. So this is the kernel code, okay, or the OS. Okay. So the mapping that is there, so let's say we call it the memory management unit. So this part of the process, so when the CPU wants to access any address that falls in this space of the virtual address range of the process, they will actually be mapped to this portion of the physical memory where the OS resides or the kernel resides. Now, what advantage do you have? The advantage is, think about this, that this is not one but two processes. So suppose there are two processes and each has its, so this is virtual address of P1 and this is, let's say, the virtual address map of P2. Now P2 will also have its kernel space, isn't it? So it will also have a location in the virtual address that will correspond to the kernel. Now, when the CPU generates an address for, say, some kernel's address space, with the kernel address space of P2, the same procedure, the MMU of this OS will also interpret that address and will map to the same kernel code. So what do we find here? What we find is, physically, this portion of P1, let's say if I represent this by this shaded line, this portion of P1 that actually resides here, this is, say, the user space of P1, and this is, say, the user space of P2. I write it in this way. So they can be in two different positions in the physical memory. This portion of the user space of P1 and this is the user space of P2. They can be in two different positions in the physical memory. But the kernel space of both of them, that can be shared. And which means that when P1 needs to execute certain kernel code, right, it doesn't have to have that part of that kernel code within this space. Neither does P2 need to have this as part of this space. So in the physical memory, you don't need to have the kernel space replicated in each one of the process address ranges. Okay, so this is the process address space of P1 in the physical memory. Even if that particular, it needs some kernel code to be executed, it doesn't require that kernel address space to be part of P1. Neither does P2 require to have that. Or for that matter, none of the processes that will be in the memory, even if they require some kernel address space to be, they require some kernel address space, they don't need to keep that kernel address space along with them. Rather, the kernel address space will be present in the kernel code, okay, wherever it resides in this, and the memory management unit, by utilizing the virtual address spaces of both of them, will ensure that that particular kernel code is shared by both processes P1 and P2. And this is how this happens, right? So you see that the kernel, the use of this virtual address space for each of the processes P1 and P2, they will contain the kernel space, and both of these kernel spaces will actually be mapped to the same physical space in the same kernel space in the physical memory. So that in the physical memory you don't have to keep the kernel space individually for each of the process, and you save a lot of space. So this is the utility of having this concept called virtual memory. Remember, it's not a concept, it's not the actual location, it's a concept. It's just a range of address locations that the OS allocates to that particular process when the process gets created. But all these ranges actually have to be translated into the final or a physical location, and that is what the OS does. Okay, so this is how the OS manages the logical address to physical address mapping. Okay, so once we are done with that, now let's talk about another interesting concept. We said that some part of the process, okay, so some part of the address space of the process is maintained by the kernel. So if you see, this part is the user space that is mapped to the actual physical location of the process in the physical memory, and this part, which is to be executed by the kernel, that lies in the kernel space. Okay. So that means this portion is actually mapped to the kernel code present in the physical memory. Okay, what do you have in this? So out of that, we said that state in the OS. Now, when a process executes, right? When a process executes, we found that there are a lot of data updations that happen, and during this data updation, the process moves through one state to the other. So you need to keep track of what is going on in the process. Okay, and this information regarding the execution of that particular process is maintained by the OS. That is why we said that the OS maintains the state of a process. And as you see, that is mapped to the kernel space. So if it is mapped to the kernel space, that means this portion of this OS is mapped to, in the physical memory, to the kernel. And now if it is mapped to the kernel, that means this piece of the state of an OS, if the process wants to know the state of an OS, the process cannot do that, because the process is not privileged to execute anything which is maintained by the kernel. So look at the problem. The process itself cannot know the status of that particular, or cannot know the status of itself, because the status of that process is maintained by the kernel. So the process has to request the kernel to provide its status. And how does it do that? Obviously through system calls. Okay. So the state of that process in the OS, which the state of the process which the OS maintains, is provided to the OS through system calls. We'll talk about that system calls in the next lecture. So now, how does the OS maintain this state of the state of the process? So what the process does is, the state of the process is maintained by the OS through a data structure called process control block. We usually call it the PCB. So this is the data structure that the OS has to keep track of what is going on and what is the state of the OS. Now what do you have in this PCB? We in this PCB have a lot of things. The first one is a process identifier. Okay. So the moment a process gets created, an identifier gets associated with that particular process. It's nothing but a positive integer that gets associated with the process. So the OS maintains the information about the process through a process identifier. We usually call it the PID. It's a positive integer which is associated to a particular process. Okay. What next? Now in addition to the identifier of the process, it also contains a pointer to the parent of the process. Okay. It contains a pointer to the parent of a process. Who was the process that was responsible for creation of this process? We'll talk about the process creation in this next lecture. So then we'll understand that there is a parent-child relation between processes, because one process gives rise to another. So if a process gives rise to another process, the one who created that is called the parent, and the one which created is called the child. So then every child must keep track of who was the parent of that particular child. So that is why there is a pointer to keep track of this. Now we keep track of the, in addition to that, we keep track of the current state of the process. We already have seen that a process goes through a number of states. It starts with new, then it goes to ready, then it becomes run, then wait. So the OS keeps track of what is the current state of the process. Is it running? Is it waiting? What is it? Is it ready? So it looks up into the PCB and finds out what is the state of the process. Then we have something related to the information related to the files. So whether the particular process has opened any file or not, and it keeps a list of this. So in addition to that, there are a lot of other things. We will gradually see what this. And okay, so one more. Now we have an information related to scheduling. Okay, that is which processes are in which state and who would be the next one to be get executed on the CPU. So all this is what is maintained in the PCB. Okay. So this is what we have as an introduction to the process. So let me quickly recap what we covered in this lecture. We first defined a process, that is a program in execution. We said that a process, if it has to execute, will first have to be loaded onto the the memory, and then it has to be the CPU has to be instructed to execute that. Now, when we load that particular the program into the memory, the code and data, they get loaded onto the memory. But it's not only the code and data that resides in the memory. The OS, before the program starts executing, the OS makes sure that the process has been allocated sufficient space which it will be needing during execution. For example, it needs during execution the process may need something to be stored onto the stack. So the program stack will be needed. As a result, the OS allocates some space for the program stack and makes it available to the process. It may need some dynamic data to be stored, so it may need some heap. So all this space that this process may be needing during execution the OS makes it available to the process, and then the process becomes ready to be executed, and when the CPU is instructed, it starts executing, and during execution the CPU makes use of all this space that has been allocated. Somewhere it keeps something related to stack, something related to heap. So this is how the process starts execution. And every time a process is created, there is a range of address locations that is allocated to it. We call it an address space. And we also saw what constitutes this address space. Okay. Then we moved on to understand a concept called virtual memory, which is very, very important while understanding about multiple processes. And we saw that when this memory image is not sufficient to fit into the physical memory, or maybe you like to have two processes, two memory images of two processes to reside in the memory and the physical memory at the same time, whereas you don't have sufficient space to hold both of them. The solution was that we brought these memory images in chunks, and a block of memory image was residing in the memory at a certain instant of time. But it was very difficult then. This kind of, if the entire memory, if the entire process memory is not available, if there's only some part of that which is available, it's very difficult to program such kind of, or to access such kind of programs, because the CPU would not be able to understand what is the actual location. In that case, the OS comes to the rescue and it creates a virtual view of that same process. That's one more view of the process. But this time, this view, which is seen by the CPU or the programmer, this view does not have any such divisions. It does not have any blocks. It's actually one complete memory block that is allocated, and all these locations which are there in this view are all contiguous, that is one after the other. And this view of the memory is called the virtual memory. It's not physical, the actual location of the program. It's a view as seen by it's a concept, and it's the view as seen by the processor or the CPU. So CPU puts its request or some address for an instruction, assuming that it is available from the view it is seeing, that is the virtual memory. But the OS notes that this is not the actual address, so it interprets the virtual address, it translates that into physical address, and then it accesses the instruction from there and it makes it available to the CPU. And we saw how by the use of a concept called paging, the CPU is able to perform this translation, where this virtual memory is divided into a number of blocks called pages. The physical memory is also divided into a number of blocks called frames. And by looking at a table which contains a relation between the page number and the frame number, the OS is able to find out that an address corresponding to a particular page belongs to each frame. And finally, we discussed about the state of the OS that is maintained by, the state of a process which is maintained by the OS. We said that in the memory image, there's a field called state of a process which is maintained by the OS, and that actually means that whatever goes on in the process is traced by the OS, and the way to do it is OS creates a data structure called a process control block for every process that has been created, and whenever it tries to access or look up to a certain process, what it does is it looks up to the process control block of that particular process. And what do we have in a process control block is a process identifier by which the OS is able to identify that process. This identifier is nothing but an integer. Now, I told you that since this information regarding a process is maintained by the OS or the kernel, so the process, if it wants to see its own state, has to request the kernel to get it. So say there's a process identifier. If the process wants to know what is the process identifier, so there are system calls through which it knows. So get PID is one such system call through which the process is able to get its identifier. And there are other information that is maintained by the OS, such as who is the parent of that particular process, what is the current state of the process, and what is the information related to the files that have been opened by the process. So that is about it as an introduction to the process.